All right, so howdy, my name is Sunberg, and I'm a member of Michael's Sizzle Lab, and I'm going to give the second talk on POMDPs.jl. And so Max kind of already told you what POMDPs.jl is, and this is going to be more of an explanation of how we got there and kind of what lessons we learned along the way, and just what our experience is. And so I actually don't come from a programming background. I'm an aerospace engineer by training. And so I think a lot of you probably already know all these lessons, but I'm just going to kind of go through and share my experiences. And hopefully if you guys have other comments along the way about your experience with open source software, then let me know. So how do these open source software projects start? It kind of starts with a vision or a dream. And some of the tools that we were inspired by are Julia and CVX. So at Stanford, there's this great course called Convex Optimization. I think they have a version at Berkeley too and stuff. And you get in that course and you use this tool called CVX and you see it and you're like, yes, this is the answer. This can solve my problem so easily. It's so flexible. It's great. And then you start looking at your problems and you're like, okay, I can make a tool like that for my class of problems. And so that's kind of what we were trying to do with POMDPs.jl. If we could get all of the best algorithms together in one place where you could use them side by side, switch things out, and everybody could kind of work together and play together in this space. But in order to do that, there are a lot of challenges. And so one way to kind of think about that is what are the most risky elements of the project, or what are the hardest problems. And so this is something that they do a lot at Google X. Astro Teller is the captain of moonshots at Google X. And one of his goals is to systematize innovation. So he's trying to work on ways to make innovation something that you can reliably count on to happen. And one of his kind of pieces of advice for that is to always ask yourself, how can we kill this project? And if you can't find a way to kill it, then it's probably a good thing to pursue. So for POMDPs.jl, I kind of saw three things that could really cause it to be terrible. One is lack of functionality. So if people can't do what they want to do, then it's not a useful software package. Another is poor computational performance. So if you start with tiny problems and they work great, but you start moving to bigger problems and they're too slow, then it's not a useful tool. And then the third one is lack of understanding. So if the interface isn't clear enough, no one is going to use it, no one's going to be able to benefit from it. So I'll kind of go through what we learned in addressing these problems. So first of all, one interesting thing with POMDPs.jl is that we have a lot of different kinds of users. So we didn't want to make this a tool where we wrote all the solvers and other people wrote the problems, or a tool where we have a bunch of toy problems and we want other people to write solvers for it. We wanted it to be both. And really, the motivation for that is a combination of laziness, which all programmers should have a good amount of laziness, and wanting to share the joy of doing the interesting things. So we don't want to spend the time to implement all of the solvers, and we don't want to spend the time to implement all of the problems, but we want to let other people do that so that they can kind of learn with us and participate with us in this. So what we wanted to do is provide this common interface so that both solver writers and problem writers could communicate. And we quickly realized that it actually wasn't sufficient to have one POMDPs.jl interface, because a lot of the best POMDP solvers in use today use is there a laser pointer? Does this work?
Yeah.
Yes, okay. A lot of the best POMDP solvers out there, such as Sarsa, and some of the classical ones like POMDP solver or QMDP, they require an explicit model of the POMDP. So that means explicitly defining the transition and observation distributions. And it's easy to do that for some problems, like the simple ones like a tiger and rock sample, for example. But for bigger problems, say you're trying to tackle the problem of how to drive a car on a freeway, it's almost impossible to specify the transition distributions explicitly. So in that case, you just want a generative model. But we also want to deal, if we have an explicit model and we want to compare another solver to SARSIP, we want to be able to use those models with POMCP and MCPI. So we decided that we needed to create this explicit interface and the generative interface, and that if you created an explicit model, it would also provide a generative model automatically. And then we think that there's room definitely for more components to this. So if you have a generative model, then it's easy to make an RL environment out of that. So, you know, someday we could have a wrapper that plugs into, that makes this the same as a OpenAI Gym environment, and then you can use all the deep RL methods. Or we could also have a more specialized interface up here, a factored interface, so that a solver that takes advantage of some special structure of the problem can live up here, but you can, if you specify your problem with the factored interface, you can also use an explicit but unfactored solver or even a generative solver just to compare. So we want this to be an ecosystem that we can build on. So what the problem writers are going to ask are, can I do what I want to do? Can I express my problem? And if you can't express your problem, then they're not going to be able to take advantage of the software. So there's a lot of different types of POMDPs that people consider. There's continuous and discrete types, which the solution methods, some of them can be used for both, but they look a lot different in some cases. So Julia helps us out with that because it allows us to define custom types for the space. So if we have like a really complex state, we can create a composite type. So like this is a car driving on a freeway. You might have all the other cars on the freeway, and then you might have, you might want to be able to tell whether it's been terminated and maybe why that's been terminated. So this will encode the discrete part of the state and the continuous part of the state in the same type. Julia helps us out a lot with that. And then, like I mentioned, we have this explicit or generative kind of distinction too, and we want to contain all of that in POMDPs. So that was a challenge. And then one little anecdote that we ran into is we started out with a ton of abstract types. I think we have like 5 now. We started out with probably 8 or 10 or maybe even like 12. So we said, yeah, we want people to communicate what their state type is. So we created an abstract state type. But unfortunately in Julia, in order to inherit from that, there's only single inheritance first of all. So if you make a type for some other purpose, it can't be a subtype of state. And also you end up, when your state is simple, like a Boolean value, you end up making a ton of these wrappers. And so it's just not that efficient. The new way is that we got rid of those abstract types and we just put the state action and observation types as parameters to our abstract POMDP type. And so I guess the lesson to take away from here is if you don't need the structure, it's sometimes better to leave it out, especially in a dynamic language like Julia. So don't over structure your interface. So the other question, so on the other side of the aisle, I guess, is can I express my algorithm? So say you have an algorithm that you want to write, but it doesn't look like our interface, then you can't use our software, you can't use our problems. And so there's 2 big different types of solvers in the POMDP world. There's offline solvers, which this is an example of a policy for the crying baby problem, where the baby can either be crying or either be hungry or not hungry, and the observation is whether it's crying, and the actions that you can take are feed or not feed. When you solve the problem, you calculate these two alpha vectors, and basically, depending on your belief, you can choose which action to take, depending on which one is maximum there. So that's an offline approach. And we provide the solve function to solve before you're actually executing the policy. Whereas an online approach calculates from the current belief state and only takes into account the belief states that you might reach. So the most popular method for that is constructing a tree. So we had to think a lot about how do we provide the infrastructure to implement both offline and online methods. And then another thing that we started out with a very narrow definition of, but came to a much wider definition is beliefs. So we started out with this idea that a belief is a distribution over the state space. So the only way it should be represented is by these probabilities. But then we started implementing solvers and we got to something like MCDI, where your policy is a finite state machine made up of these nodes, and you can't see that at all, sorry about that. But there are some nodes in there, and those nodes are tagged with actions, and each of the edges is tagged with an observation. So to execute the policy, you actually just traverse this graph. And that is not a probability distribution over the states at all. It's totally different. Your belief is actually just which node you are in the graph, so what state you are. So originally we designed our belief updater so that the thing that defined the belief updates was the POMDP itself. And we quickly realized that that doesn't make sense for all the solvers. So we introduced a whole new concept called an updater, which could be implemented by the person writing the solver if it's specialized for MCDI, or it could be implemented by the person who's writing the problem, could write an exact belief updater. So we ended up having to make it more modular so that we could accommodate these things. And I guess maybe the takeaway from this is you want to be as simple as possible, but not simplistic. So our original idea of what a belief is turned out to be simplistic. It was overly simplified and didn't actually capture all the things that it could be, which is a state for the policy. Another question people will ask is, can I use this solver? So we want to be able to use solvers written in other languages, and we've had some success with that. Obviously, so if you have an explicit model and you want to use a solver like SARSA for POMDP solve, that's easy to do because you can just export the files. Generative models, we would like to be able to use the C++ implementation of MCDI, but right now we can't because we haven't figured out how to implement C++ calling Julia in a parallel environment. So that's still work that needs to be figured out. Another thing that's really common is, can I use my special trick or heuristic for this problem? And this takes a lot of thinking on the part of the solver writer because there are just a lot of possible forms that heuristics can take. So for example, with MCTS, you construct a decision tree, and at the leaf nodes of these decision trees, you have to have an estimate for the value. And that can take many forms. So we use this software a lot in the AA228 class in the fall. And so usually in MCTS, you'll do a rollout. So I want to be able to say my value estimate is a rollout with any specified policy. But some people in the class also had an offline estimate of the value function that they had calculated for their states. So we want to be able to make the value estimate some function. So you can define anonymous functions in Julia with this syntax. So we want it to be also be able to be a function, and we also want to, if you're just playing around with it, you want to be able to put a number in there, even though that doesn't really make sense. And in fact, that would be, well, that might be useful in some cases, but we don't want to limit what the kinds of tricks that you can use in heuristics for your problem. So that takes a lot of thinking. And it also takes a lot of thinking to have this flexibility, but also make it fast. And I'll talk a little bit more about that in a minute. Also, so particle filtering, you almost always have to use a domain-specific heuristic to get it to work well. And so we want to be able to accommodate all the things that a user might want to do. So the next challenge is computational performance, and Julia helps you a ton because it's an excellent language for being expressive but also fast. And two of the tools that are really important if you start using Julia are the profiling. So you can profile any Julia code and it will give you this flame graph that shows how much time you're spending in every function. So that's been super useful for us. But also, in order to be fast, the compiler, this isn't enforced in the code, but implicitly, in order for the code to execute quickly, you have to be able to determine the concrete types of all the variables at compile time. So they give you this nice tool called code warn type, which if you use Julia and don't know about that yet, you should definitely check it out because it has given me 10 times speed ups when I can identify exactly where there's type ambiguity. So in this case where we're trying to be flexible, this value estimate is a parameter of the solver. It can be either a float or a function or a rollout, and you have to parameterize your types really smartly in order to give the compiler information about what that will be while still being flexible. So if you ever are using Julia and want some advice on that, definitely talk to me or Tim or Max. And then, so one kind of lesson that we learned is not to prematurely try to optimize performance. I know everyone says that in programming, but it's totally true, and it killed us at the beginning. So one red herring that we spent a lot of time following was pre-allocation. So if you come from MATLAB, if you come from a lot of other languages, it's really important to pre-allocate all your vectors for performance. And it turns out, so our idea for doing this was to put an optional argument at the end of every function that allowed you to feed in a pre-allocated state. So the solver writer could call generate_s, which is the function to generate the next state given the current state and the current action. And the solver writer could either pass in a pre-allocated state that they had already made room for, or could just leave it up to this create state function. And this was extremely confusing for users, extremely confusing to coordinate between solvers and problem writers because this is an optional argument. And it actually didn't cause that much of a performance increase. And we realized, the main thing that we realized is that if the state representation is efficient, allocation should really only be a small part of the calculation. So if your state is like a huge image, either you can make it more efficient by only storing part of that image, or you're going to be setting every pixel of that image anyway, so the allocation part is not actually that huge of a problem. And these kind of optional arguments in interfaces are not good for communicating between solvers and problem writers at all. So then the biggest challenge, so I think with the usability challenges, we've done really, really well. And with the speed challenges, we've done really, really well. There's never been a time when I have run into a point where I can't express my problem or I can't express my solver. And we're getting the same kind of performance as C implementations of these solvers, at least in the same order of magnitude. So I think computationally and functionality-wise, we're doing great. Communication is where we're having, I think, the hardest time. And that comes from a variety of reasons. So first of all, many people aren't that familiar with Julia. And that's just what happens with a new language. We think it's great, but not everyone has used it before. And then this has been really hard for us. So since Julia is a dynamic language, even though it's just a time compiled, it still uses this kind of duck typing. And that means that there's no built-in language features that check if you've implemented an interface. So we can't, in the code, specify, oh, you need to implement these functions for your problem to work. We have to do that only in documentation. And that is really, really hard, especially if the interface is changing. It is hard to make sure your documentation is exactly the same as your code. Also, so POMDPs can look a lot different for a lot of different users. If you have a continuous generative POMDP, that looks totally different from a like table-based discrete POMDP. There's also many types of users, like I talked about before, and it's also, we've had a lot of trouble with defining the right names for things, especially boolean. And another thing that happens is solver writers have a tendency to take an example problem that they're trying to solve and build a solver and example problem together. And it doesn't actually conform to the interface, and there's no automated way for them to, no automated way for us to like check if everybody's interpreting the interface correctly. So that's been a challenge. And then I also have some experience from AA228, which is a class that we offer, and a lot of students use this. Things to do: keep your code concise and simple, but not simplistic, like I said before. Use examples. This is always what I've heard a lot of people say about this, and also asking about other kind of software frameworks like RLLab and stuff is what is the minimum I have to write to get it working? And RLLab that's like a really great thing about OpenAI Gym and RLLab is like you can see it all in one little code snippet. But ours is, that question has a different answer depending on what type of problem you're going to have to write, and so it's like sometimes a hard question to answer. And another thing is to make clear what's going on. So if a student writes code and it compiles, it could still be doing something that's totally different than they expect, and you need to have some kind of way to like visualize that or tell the student that it's not doing what they think it is. And then also make sure they have a conceptual understanding of the different kinds of problems. So like that graph that I showed at the beginning, there's factored MDPs, there's explicit POMDPs, generative POMDPs, and then like an RL environment. And those are all kind of different, and it's hard for students to understand that at first. So making sure they understand the concepts behind your software is really important. And then these are my experiences from collaborating with other developers on this project. Like I said before, resist premature optimization, resist the urge to define too many interfaces and features like the abstract state types and stuff. Then use testing and examples. You can use intuition at the beginning, but you really want to test all your decisions and see if they actually make a difference. So like our premature optimization with pre-allocation, we could have gotten away from that a lot faster if we had done some tests. And also, when you're working with other people, it's good to just write out a whole bunch of test use cases and have everyone agree that this is how the software should work, and all conform to that. That's something that I found to be really useful. So the last anecdote is this, this kind of requirements system that we made. So this is built to answer the question, what do I need to implement to use this solver? So a problem writer has this idea of a problem in their head. We say, oh, implement a POMDP type, and then what parts of the interface do they need to implement? And if they get that question wrong, it can be a disaster on either side. Because if they think that they have to implement the explicit transition and observation distributions, for some problems you just can't do that, so then they can't use the solver. And if they think that they only have to implement a generative model or a few of the functions, then they're not going to be able to use it because it just won't work. And initially, all our solvers just had kind of a list in the documentation of which functions they use. But that turned out to be also extremely confusing because sometimes there's different types. So what we ended up having to do is use Julia's really excellent metaprogramming to make a tool where solver writers actually it doesn't actually analyze the code, which is what we wanted to do eventually, but solver writers can use this syntax to indicate the exact methods that users need to implement to use their solver, and then it will print out this nice warning message that shows which methods you've already implemented successfully and which ones you're missing. So the takeaway here is, like, sometimes you don't want to be too simplistic in your answers to questions. Sometimes you have to make a relatively complex tool to even answer questions. Or maybe that's just what we get for using Julia, because it doesn't have built-in interfaces. So anyway, and then the final step is just like keep an eye on what users are doing, because one, it gives you like a feedback loop of what you need to change, and then it also like will show you the fruits of your labor, I guess. So we had a bunch of the AA228 students used this software for their projects, and at the end we chose the kind of the 5 or 6 best to like give awards to, and I think 5 of those 6 had used POMDPs.jl. So that was good to see that it actually resulted in very good educational projects. And that's all I've got. So thanks for your attention. I don't know if anybody has any questions or comments, or like, why did you do that? That was stupid. Yeah.
Sorry, the terminology is generative versus what's the other?
Explicit. That's terminology that we made up.
Yeah, fair enough. Well, no, it's a problem that I also grappled with. And after thinking about it for a long time, I thought the answer was to use a DBN, but to specify the transition probability as a probabilistic program, because you're actually writing down the explicit sort of sampling instructions, right, that you would do the sampler, but you can compile that probabilistic program into a distribution for use in generative models. So I really thought that was the way to not have to decide.
Yeah.
So would you consider it, or would you have an argument against that?
Well, so I'm not sure exactly how that would look. I'd have to so I don't know if I could comment on it, but I would say that if you have a really complex problem, like a freeway, so like let's say you have a complex problem, like you're driving on a freeway or something, and in your simulation step, you have some kind of noisy thing that happens, and then some other dynamics that translate that into something else. I guess, so probabilistic programming languages, you're saying, can handle that, where you have like some distribution that is difficult to specify. Like it starts out with a normal distribution or something, but then goes through some dynamics that make it some other distribution.
Yeah, so you're probably getting at one detail which would be difficult, which is if you have lots of events that spawn other events and you actually can't bound the number a priori, then you get into like non-parametric probabilistic programs, and then I have no clue how to compile those things.
Yeah.
You know, into the literature process or something.
Right.
So that's probably where then you do want to diverge.
Yeah.
If you have like tons of events and you can't count them a priori.
Yeah. And I also think that it's so one of the things that one of the decision factors that decides whether somebody is able to take advantage of this software is how low the entry barrier is. And so by adding a generative models interface, I think we've lowered the entry barrier a lot. So somebody can get something complex, even if they could eventually implement it in a probabilistic programming language, it's a lot easier to get something up and running, watch it being simulated and stuff, with just writing a generative model.
It's, what are, give me some examples of generative models. You have probably discrete, normal.
Well, there's, I mean, so it's all you have to implement is this one function basically, generate, well, one or two functions, generate S or generate SR if it comes with the reward, or generate SOR if it comes with the reward and observation. So any problem that just requires a simulation, like all you have to do is write a function that takes in the MDP, the current state, the current action, and a random number generator, and outputs the next state.
Oh, so sorry, you're using generative. So,
I may be using it.
So when you think of generative, I think of distribution.
Oh, no.
Okay.
Yeah,
this is
okay. Is that, so maybe we need to talk about the terminology, because we don't want to, I don't want to like confuse a lot of people. But we're thinking of explicit as explicit probability distributions and generative as sampling.
So I'll find out, look at a bunch of examples,
Okay.
and just see if there's an easy way to do it.
Yeah.
On the program. It's very nice formula, which others invented.
Yeah. Cool. Thank you. Yeah.
Maybe I just want to pitch in there. I was also confused about the terminology generic versus explicit, because I understood the same generic as being this generic model versus a discriminative model.
Oh, okay.
Right. But I think what you call generative here, I mean, you could call it like that because you can sample from it, right? You just don't have an explicit model as you use the term. But yeah, I was wondering actually if you get confused questions a lot about this terminology.
Yeah, basically this terminology came from the POMDP paper, where he said, so like most, like SARSUP or something, a value iteration time solver uses an explicit model, but so like POMDP only requires a single step generator simulator, and people in that literature sphere use generative model to just say something that samples from it. But yeah, thanks for the comment.